So as Madalena said, geology is geology, and the geology underpins everything that we do in terms of critical raw materials. And so we're going to move into our geological talks now. And I'm really pleased to be able to welcome our first keynote, Erik Jonsson from the Geological Survey of Sweden. Erik and I have been working together for some 10 years or more on overview of critical raw materials across Europe. And recently, Erik has really led on the sort of overview of critical raw materials in the Nordic countries. And so today he's going to talk to us about how the Nordic part of Fennoscandia can be a potential treasure trove for critical raw materials. Erik.
Thanks so much, Catherine, for that kind introduction. Guess we should be going into it then. Nice to see you all here. That was some original presentation for the social media, I think. So, the Nordic part of Fennoscandia, potential treasure trove for European critical raw material needs, or, well, hopefully by the end of my talk you will be, if you were not initially, convinced. So, the outline of my talk will be something like this, a bit of fundamentals, starting really at the key issues to the thing. I will take you through an extremely crude and brash sort of walkthrough of the geological evolution and, to some extent at least, critical raw materials metallurgy of the Fennoscandian shield. I will also make some hints towards the necessity of adding Greenland also to the Nordics. Hey, Jakob. I'll try to get into a few of my own personal views on how we need to think about critical raw material exploration and research in the Nordics today. And I'll finish off with a few little highlights and conclusions, summing up, not least, what we see today of the current known and well-defined, reasonably so anyway, critical raw material potential in the Nordics for particularly green technologies. So I'll try to tie in where Madalena stopped, really, just looking into the world situation. This is a map that is a few years old from the SGU. Seeing the all-dominant pie over there in the east, and wanting to really start here with our dire situation, if I may say so, raw materials wise, seeing that all of the pies in Europe are actually mostly refined materials, so imported raw materials rather than primary production. As a geologist, of course, I like to think when we talk about critical raw material supply, I think about primary production because I think about geology. I think about minerals, yes? So that seems to be the overruling thought among many of my colleagues, but of course, and I'm happy to see that there will be a session also tomorrow about this, what happens after the primary production from a mine? Can we handle the downstream steps, the refining, the making of the concentrates, the intermediary products, and even magnet materials, whatnot? No, we can't in many cases. And unless we solve those issues, most of these metals will remain just as critical as they were last week, even though we perhaps might start to produce them in Europe, including the rare earth elements. So yes, dire straits. Yet, we have a reason for being here, yeah? And that's, of course, that if we talk about critical raw material geopolitics, it is actually all about geology. I am happy that someone mentioned antimony the other minute. Madalena. Close to 80% at this point of reporting coming from People's Republic of China. Why is that so? Why is that changing? Why did we have that sort of cut downs and threats when it comes to international antimony supply? Well, of course, it's all in the geology, right? Do I see nods here? Yeah? So. Well, it's because China's had the opportunity of mining low temperature, shallow, continental hosted hydrothermal stibnite deposits for ages. Deposits that were mined out in Europe by the year of 1900, basically. And they could mine them at the small scale. Now that is more or less systems that are worked out today. They are more and more leaning towards byproduct production of antimony from much more complex gold deposits. Hence, they are facing declining local supply. There we go. So it's all about the geology, eh? And I really want to start here. This is a plot I like to throw out whenever I give talks about this. Eh? The average elemental abundance is in the upper continental crust normalized to 1 million atoms of silicon, because silicon is the most common metal we have basically in the crust and in the mantle. What does it tell you? Well, it tells us that we have the common elements up there in greens, the rock-forming ones, the one forming most of the rocks that we have around us, particularly if we look at the continental exposures of crystalline bedrock. We have the rarest metals down there in yellow, including gold, platinum group metals, and some semi-metal like tellurium. And then we have the rare earth elements. Always coming back to the rare earth elements when we talk about CRMs and our situation with those. Typically, geologists classify them as yttrium, all in blue here, plus the lanthanides. If you ask a chemist, they will include scandium. Geologists do not, because scandium doesn't follow the rest of those metals in geological processes. Hence, we tend to kick scandium out. What about abundances then? Rare earth elements, where does it come from? How many in here knows the background to the word or definition on rare earth elements? Up with a hand. 1, 2, 3, 4. Okay, not many. I will not explain it. Talk to me later. Suffice to say that they are not that rare, at least not in the upper continental crust. You can see that here. The most common ones like cerium and lanthanum are on par with base metals such as copper and zinc, and even the rarest ones, lutetium, for example, is similar, even more common than our just talked about antimony. So this gives us clues, these average abundances, to the intrinsic problems for having geological processes actually concentrating those meager levels up to something that can be economically mined. Not just having a resource is not enough. It has to be proven economical to mine. Otherwise, it's not really relevant, is it? And we have to know more about these components. This is a plot of, on the x-axis, ionic radius, on the y-axis, cation charge. Sorry for all non-chemists in here, or non-geologists, but we need to think about these things. This is the fundamental issues that will govern where to look for, in the end, our critical raw materials. We can see the lower end of the HFSEs, the high field strength elements here, with a major part of the rare earth elements stretching into the LILEs, the large ion lithophile elements. We have other elements up there. We have critical tantalum, tungsten, hafnium, among others, with higher cationic charges, slightly smaller ionic radii. They're all staying outside of the blue field being mantle rock-forming elements, the ones that we can equate also with the common rock-forming elements in most of the crust. We have the elusive and superlight beryllium and lithium with low cationic charges and small ionic radii down there. They're all staying out of the commonality of ferrous metals, many of the base metals, and our rock-forming elements. They are what we call incompatible. I'm sure that some people here will come back to incompatible elements. I hope, Catherine? Maybe. Axel, maybe? No. Jakob? Okay. But this means, what does it mean? It means that in order to understand the geological processes on all scale, from plate tectonics, super wide, super large, super big, over millions or billions of years, we have to understand the functionality of single metals and other elements, how they interact, how they form minerals, how they will collect through geological processes such as partial melting, fractional crystallization, hydrothermal processes. That's the fundament if we want to understand where to go for our critical raw materials. And this is also the fundament for a map like this one. Admittedly, not the most beautiful one you can have. It's supposed to be updated fairly soon. This is the former Fennoscandia ore deposit database map, now renamed Nordic ore deposit database, as we threw out Russia for obvious reasons in the collaboration. This shows, and this goes just to prove, our focus up to now on just plain traditional metals. Most of these fields are base metals of various kinds, ferrous metals, certainly a few precious metals, but a minority of the fields are what was in this case classified as special metals, most of them actually critical metals. We have been focusing a lot on that. We have hundreds, if not thousands of years experience in mining and concentrating those metals, but not of the ones we are looking for today and have been looking for perhaps for maximum 10 years or so, 15 if you're lucky. So we translate this into geology then. This is where we go. Fennoscandian shield. And if you want also potentially in some, cases including Greenland, seeing that we have this mosaic of geological formations, the formations starting way before 3,000 million years ago and ending actually with sedimentary cover units younger than a couple of 100 million years. A long geological history, which I will not go into super detail, but I have to sort of run through it at least. But the major story that I want you to think about is that this long geological history, really complex, spanning over a long time, and very, very contrasting pressure, temperature, and whatnot conditions, led to a really great diversity in both rock types and then, of course, also mineral deposits hosted by those diverse rock types. That is really why the Fennoscandian shield and associated terrains is comparable to extensively mineralized terrains globally, such as Australia, Canada, Brazil, if you like, and if you let me to. So we start in the Archean, represented mainly by the northwesternmost part of Russia and eastern and northeastern Finland. It's actually not that much. It's great for exploration in general, for critical raw materials, perhaps rather sparse potential. If we move into the latest part of the Archean and into the earliest stages of the Paleoproterozoic, so straddling this 2,500 million years border, then we start to see interesting things. Really significant critical raw material potential with platinum group metals, PGMs, cobalt, vanadium, titanium, strategic metals, which are not really classified as critical, if you ask me, but that's another story. You can take that later as well. Byproduct metals, and with byproduct metals, I mean the ones, for example, like bismuth, antimony, indium, gallium, germanium. A really benchmark in this situation when we start to rift apart and break up the Archean then existing continent is the appearance of the gigantic Siilinjärvi carbonatite dated at 2.6 GA, so just a wee while before the end of the Archean. This sets the note for basic, mafic to ultramafic layered intrusions containing chromium, platinum group metals, noble metals, etc. And this goes over then into the peak stage, really, of crustal formation during the growth of the Fennoscandian shield. And that's what we call alternatively the Sweco-Karelian or Sweco-Fennian orogeny. If you ask people in the GTK or the SGU in Sweden, you will get slightly different usages of this terminology, but it's basically the same. It is a huge amount of crust that is being formed and built into this growing continent during this fairly short geological stage, only about 200 million years. You have to be a geologist to think that that's a short time period, right? We have huge amounts of diverse critical raw materials being formed as deposits here. Rare earth elements, arsenic, cobalt, phosphorus, titanium, vanadium. Well, we have the strategic copper, nickel, bit of manganese, graphite, fluorite, various byproduct metals. And then we also have, as I know that Catherine will come back to later, the rare metal pegmatites with their potential of lithium, beryllium, tantalum, niobium, now also feldspar critical mineral, less so the rare earth elements. This is huge. This is my everyday sort of working place, the Svecofennian or Sveco-Karelian orogeny. As things evolve, going from past the Sveco-Karelian orogeny into also Meso and Neoproterozoic times, even starting to get close to the Phanerozoic, we see various more dispersed deposits occurring here, but nevertheless really important ones, including, for example, gigantic titanium deposits in Norway like Telnes, Skutterud, Modum, cobalt deposits, historic but still, the major Fen carbonatite complex southern Norway, the Norra Kärr deposit, Ni43-101 classified, huge heavy rare earth element and rich deposit in Sweden, that's about 1.5 GA, and the mysterious and unique Olserum system in southeastern Sweden, to mention a few. Finally, in the Phanerozoic, we have just a little bit of intrusive activity. Most of the deposits that we get here are related to outboard terrains, including island arcs and ophiolites and sediment-hosted deposits being thrust upon the Svecofennian crust. This is really chippy, actually. Can you see this when I'm... Nah, I thought not. I should have this long stick, that's what I like. Whip around, you know. We have up there to the northwest, we have the Caledonian orogenic belt in gray anyway, that was thrust on top of the Fennoscandian crystalline bedrock, and that made the preservation of all those deposits from the outboard terrains possible. So we have quite a lot there from polymetallic sulfide deposits, from the island arcs and ophiolites. We also have from the deep water reduced sedimentary environments, in particularly the Swedish side of the Caledonides, shale-hosted uranium, shale-hosted rare earth elements with phosphorus, shale-hosted vanadium. Big deposits typically, but with low grades. Quite diverse. And to cap things off, we have the potential superplume event forming the biggest alkaline complex on Earth, as far as I know, and that's the Umbosero-Chibini complex of the Kola Peninsula, with associated carbonatites at Kovdor and luckily also Sockli on the Finnish side of the border. So despite this, there is a lot that we do not know really. It's hidden. If you've flown a beautiful day like this over much of Sweden and Finland, you know how it looks. It's just green. And below the green stuff, you have till. So it's hard doing exploration in many of these areas. And for some deposit types, we certainly do not know how to do it yet. I'd like to just throw out some balls here. Sorry, pies? No. Brownfield versus greenfield exploration. Classic terms, at least for exploration, is brownfield, meaning that we are exploring near to the mine. Doing it actually, as it were, in the shadow of the head frame, like this old head frame from the Bergslagen province in Sweden. Well, we don't have any traditions of mining of these new metals. So we have almost, I should say, no brownfield to go to, except for particularly some byproduct metals. We have to think about the new non-traditional metals and minerals. as green fields, pretty much of it. And that demands new knowledge, new thinking, new technologies for sure. We might even need to develop new deposit type concepts. What do I know? And some of recent discoveries might force us to actually reinterpret some of the geological process and evolution as we have considered them previously. What about those strange deposits that could be new types of deposits? Well, how about unconventional lithium deposits? Not spodumene petalite, LCT-type pegmatites, not salar deposits from young high places like the Andes. Do we have them? No idea whatsoever, but should we look for them? Yes, definitely. What about metamorphosed laterite deposits? The biggest contender to come out producing rare earth elements from outside of China after the crisis of 2010, 2011 was Mount Weld in Australia. That's a carbonatite laterite deposit. They're not mining the primary carbonatite. That's pretty crappy as an ore, actually. But the laterite on top of it is great. How do they look if they get regionally metamorphosed and tectonically deformed? Who knows? No one has described one yet, maybe. Higher grade scandium deposits, do they exist at all outside of few small rare element pegmatites? I don't know. High grade hydrothermal graphite, they exist in other parts of the world. I know that in Finland there are a few ones, but they're tiny. Can we find big systems, economical systems? Good question. Still, we're not doing that poorly, really. Spodumene from recently discovered Bergby pegmatite. We are seeing upgrades in our knowledge about several deposit systems. Sockli carbonatite in Finland, Vittangi graphite, northern Sweden. And these days, everyone seems to be the ones having Europe's largest deposits of rare earth elements, yeah? Kind of silly. I mean, Fen was at the core of actually acceptance scientifically of carbonatites as an intrusive rock in the middle of the scientific infighting of the day. That's the first part of the 20th century. This discovery by LKAB was actually published in 1931 by said Per Geijer, an eminent geologist of the time, had wet chemical data that pretty much replicates the data that they went out with big hullabaloo the other day. So, new and unexpected discoveries then, that actually, yeah, this is biased, this is looking from my side of things, Sweden, a few Swedish examples, just to show that there are a lot of things out there, geologically speaking, that we do not know, that we can discover. Ulserum Djupedal vein-type rare earth element deposits in southeastern Sweden. I showed you that on the map just previously. Originally mined for iron. Now, an ongoing exploration target with an NI 43-101 classification for rare earth elements. Bergby system, starting as a student boulder find in 2007, first hit by a drill core in situ 2016, now ongoing exploration, going from a single dike 2 years ago to now known swarms covering at least 60 square kilometers. And then, perhaps the least interesting economically wise, but showing us the potential of looking the Åkersjön metacarbonatites in the Swedish Caledonides. The first, as far as I know, rare earth element niobium mineralized metacarbonatite in the Nordics that we worked on, discovered between 2004 and 2006. And actually, most people would just bypass it. It's just a nice, and not a very nice. We're also trying to take care of knowing about the secondary resources, not least as this is a politically hot potato. Perhaps not economically always very relevant if we calculate on it, but we've done our job for Sweden anyway with concentrations in the central part, in the Bergslagen province, with both dumps, so mine dumps with the coarse material, tailings, testing, pilot studying slags and burnt shales, getting some really good data sets for well, historic up to fairly recent mining sites. And now I will stand here and read you this list. Well, okay. Just highlighting here the case of rare earth elements in tailings, so old sand from concentrating plants, adding up to something extremely crude figures here. Maybe up to 49,000-50,000 tons of rare earth element metals, not oxides. Could it be used? I don't know. Summing up then, what do we have? Well, if we look at cobalt, we see that we have potential in particularly Finland, 100% of European current production. We have production of graphite in Norway and really promising projects, particularly, I would say, additional in Sweden and Norway. Going to hafnium, biggest resources in Greenland, as I'm sure someone might say something about later, but the only defined hafnium resource on sort of in Western Europe is in Norrskär in Sweden. What about lithium then? Well, I was happy to hear about this loan to the Keliber project in Kaustinen, because we say here that we have moderate potential only, but still we have an advanced project, mine project in Kaustinen, Finland. And as I've just tried to highlight, we have some new discoveries in Sweden that are pushing the frontiers of what we can actually find, I think. Niobium, particularly in the alkaline deposits of Greenland, but also fairly large potential in other places, not least in the Fen carbonatite complex in southern Norway. PGMs, really the only production in Europe worth mentioning is from Finland, and there is still outlying potential there. Rare earth elements, coming back to them, always, always, always at the core of critical raw materials, I would say, particularly for green energy technologies. You can't get away from them. And I would say that in the Fennoscandian Shield, we have the best looking deposits in what is today the EU. There are deposits, for example, in the Ukraine. 3 out of 4 are now in Russian hands. We have deposits in Turkey, but the rest are small. The big ones are here. Happy to say that. Silicon metal production in Norway and Iceland, actually, from refined materials, have great potential of developing this, as I'm sure we will hear more about, I hope. Tantalum, well, so. But as a byproduct from potential lithium production, that could be something in the years to come. Lightweight alloying, titanium. We have massive production coming from Norway and additional potential in several of the other countries. Presently, 100% of European mine production comes from the Fennoscandian Shield. Finally, vanadium, widely used for ages for alloying steel, but with the potential of stationary redox flow battery technology becoming important for harnessing and storing electric power from, for example, wind parks. This demand situation might increase significantly, and we have something like 10% of the global known resources in the Nordic countries today. So yeah, we have this that we know, and we have a lot left to discover and better define. So thank you.
Thank you so much, Erik. A brilliant whistle-stop tour of the potential for critical raw materials in the Nordic countries. Do we have some questions for Erik? Come on, I'm sure we must have.
It's like a hit and run.
Let's kick us off with I've got a question for you.
Yep.
What are the really big barriers? I mean, particularly the rare earth elements. You and I were working on them 10 years ago, and we thought there'd certainly be a mine for the rare earth elements somewhere in the Fennoscandian Shield or in Greenland by this time. And there isn't. What are the really big barriers? that are causing the problems?
Well, I would say that they are twofold. One is, of course, general slowness, bureaucracy. I'm talking about Sweden now. Utter slowness and utter unwillingness to handle hot potatoes like mining projects, particularly in the southern half. That's Norra Kärr, basically, I'm referring to. Ulserum is another problem because it's a tiny, teeny weeny bit of uranium and thorium there as well, not making things easier. So public opinion and legal decisions failing, actually, and being postponed is an issue. But the other one is really technical and economical, I would say, because of the small market that is rare earth elements globally today, with maybe up to only 300,000 tons of metal being produced, consumed yearly. That's not a lot. If you compare to ferrous metals, base metals, that's nothing. That's what we in Sweden would call a fart in the universe. En fjärde universum. So it's nothing. And that, of course, means that the rare earth element industry is really, really a sensitive system. If you open 1 or 2 new mines rather fast, what will happen to the price? If you're sitting on deposits that you want to start with that are super enriched in the cheapest light rare earth elements, lanthanum and cerium, you will overproduce them. You will have to pay people to take them because people want other rare earth elements. You want to have the medium ones, including, of course, neodymium, important for battery, for magnets. You want the heavy ones that really pay off with prices like $30,000+ per kilogram of metal instead of a measly $5 for cerium or lanthanum. So it's a tricky market, and that also makes investors shy off. So that's my take, the big thing. Then I've got some other thoughts as well, but yeah.
Hang on, Madeleine, we just wait for the microphone. Thank you.
What about the lack of processing technology
Yeah.
in Europe?
As I started off saying, I mean, they will be as critical if we lack that. I mean, if we have mine production in Sweden or Norway, for example, they will still be critical if we have to ship our first concentrates to places like what? China? Malaysia, best case. So no, yeah, we need the entire value chain. Otherwise, we're in the same boat, same sinking boat.
It is really important, isn't it? How much geology overlaps with the processing and the engineering, the public acceptance, the economics, you know, the whole story is all tied up together.
Yeah, but without the geology, nothing of the others.
Absolutely. More questions for Erik. There's one here. We have a question at the back, Pertti.
Okay, thank you, Erik. Nice presentation. What do you think about potential of kind of mining from old tailings in Nordic?
Well, I showed you some stuff that we have been doing in the past 3 years in Sweden. I mean, we haven't touched upon current mining sites, of course, because that is up to the companies. We cannot walk in as a National Geological Survey and do their stuff. We shouldn't, we wouldn't, we couldn't. But we have done this survey of a significant part of the historic to fairly recent mines. I just showed you some images of maps of this. And we get some interesting numbers, for sure. Politicians get all delighted when they see it. We don't have to open new mines. We can actually use these tailings. But can we really? Can we really? I mean, many of those tailings would need their own specialized process to handle them, to extract the various metals in there from various different host minerals. It would need to be designed specifically for that tailings or dump material. In many cases, frankly, if you ask me personally, in most cases, that would be entirely untenable unless you're mining the same kind of deposit nearby. So you already have a tailor-made process for that kind of ore. Then, yes, much as LKAB is suggesting to do with their old tailings, apatite-rich tailings, up in Kiruna, northernmost Sweden. That might actually work. But to take just any old tailings and try to make it work economically, I don't think so. So, short answer to a very complex question.
We have time for one more question. Jakob.
Yeah, Jakob Karding from Geological Survey of Denmark and Greenland. Thanks a lot for an interesting talk. What about the social license to operate? Is social acceptance, is that changing now? And do you think it's going to change now? It's high on the political agenda. For instance, Nordic, I mean, has been facing huge problems because of resistance from the public.
Yeah, it's an issue everywhere, I guess, but less so, I would say, in Sweden's case, in northernmost Sweden, where we have ongoing mining, in south central Sweden, where we've had and still has some ongoing mining, and the further south you go, the closer to the big cities you go, the more into areas where there's a lot of holiday homes and whatnot, of course, the problems arise. In the mining projects in northern Sweden, we have, for example, an iron ore deposit that has been fought about now for a decade or more, called Kallak, or Gallok in Sami. A majority of the protesters have not been local, except for the local Sami village that are afraid, of course, of interference with their reindeer herding. But the main proportion of protesters, demonstrators, have been bussed up from the major cities, from Stockholm and so on. They are not local. The locals actually get rather irritated by this behavior, as I'm sure you can understand. And this is happening in many places, at least that I have any insights of. And I think that in the end, perhaps education, perhaps more sort of conveying the messages, what this is all about, not just sort of flaunting this, that we have to mine more because we want the green technologies, but we have to mine at all if you all want to have this lifestyle, if you want to have these technologies that you're so used to. And this, I think, is the only remedy.
Thank you, Erik. And with that, we will move on. Thank you very much, Erik. Plenty of food for thought, for discussion over coffee and lunch, I think.